Okay, so for the final talk of the whole 24-hour conference, we're delighted to have Tam Cheetham-West from Yale, who will be talking about finite quotients and property FA.
Thank you so much, Alex, and for the invitation and for organizing. And as this is the last talk of the conference, I just want us to say a big thank you to our organizers for this conference. So applaud, use your reaction emoji. Yeah. So I want to talk briefly about finite quotients and property FA. And the most important thing I'm going to say is that this is joint work with Alex Lubotzky, Reid, and Ryan Spitler. So groups, right? We like to study groups via their actions. That's like a very recurring theme, The simplest kind of action like one can think about is like the action of a group on a finite set. And that's encoded by a finite quotient of the group. And in particular, the groups I'm thinking about for the purpose of this talk are groups that have lots of interesting actions on finite sets. These will be countably infinite, residually finite groups. And in particular, for every non-identity element, right, there will be a finite quotient in which this element survives. Okay, and a lot of work has gone into understanding groups via their actions on finite quotients. Finite quotients correspond to finite index normal subgroups of the group. Another kind of action that groups have is like actions on simplicial trees. And whenever we have like an action on a simplicial tree, that is non-trivial. And what does non-trivial mean? Non-trivial means like the whole group. So here it means like no global fixed vertex, right? Non-trivial actions in this sense correspond to non-trivial splittings of the group as a graph of groups. Okay, so sequence of free product amalgamations and HNN extensions. And when a group has no non-trivial action on a simplicial tree, equivalently, no non-trivial splitting, such a group is said to have a property FA, and property FA was first defined by Serre. And in particular, good examples of groups with property FA, like you have the fundamental group of what we call a non-Haken closed three manifold. So that's one flavor of example, because where we have this picture on the one hand, which I can put up here, right, is we have actions on trees, splittings of groups. If you are in the three manifold case, by work of Waldhausen, Epstein, and I should also say Stallings, this exactly corresponds to your non-trivial splitting corresponds to existence of an essential embedded surface in your three manifold, right? And so another flavor of example of groups with property FA is like the example of groups with SL3C, and in particular, Margulis shows this. So this is in Serre's book. But in particular, Margulis shows that anytime you have a lattice in a higher rank Lie group, that lattice cannot and every action on a tree, a simplicial tree, will have a global fixed point. Okay, and so the main theorem of this talk is that it relates actions on finite sets to actions on trees. And it's a family of examples indexed by the primes. And the statement is that you can have two groups, two residually finite groups with the same finite quotient, but one acts non-trivially on a simplicial tree while the other does not. So let me go and talk briefly about actions on finite quotients and the set of finite quotients. The first very important observation is that the set of finite quotients does not always determine countable groups up to isomorphism. We have these nice historical examples due to Gilbert Bumslag from 1974, where we have these two groups, gamma and delta, which is which are sort of like HNN extensions, cyclic extensions of Z mod 25Z that have the same finite quotients, provably, but are non-isomorphic. So the set of finite quotients, set of finite images does not always completely determine the isomorphism type of the group. And this is just like one flavor of example. There are lots of different flavors of examples of non-isomorphic groups with the same finite quotients. But the big question is if we know and we're able to somehow certify the two groups have all the same finite quotients, right? What can we say about the groups, right? How alike are the two groups, right? And so there are some answers. We have some answers, and there are some things that we can say. So for example, we can say that the two groups have the same abelianization. And this is because the abelianization is sort of like the maximal abelian quotient of the group, and finally generated abelian groups we can show are completely determined by their finite quotients among all residually finite groups. And so we can say the groups have the same abelianization. That is not always, that's a good invariant. In practice, it's very helpful, but can we do better sometimes? Yeah, and more interestingly is that we have like a correspondence theorem, like the finite index lattice structure of both groups is the same. In particular, you will have, when two groups have all the same finite quotients, there is like a correspondence of their finite index subgroups, a correspondence of indices, a correspondence of normality, a correspondence of there's a full correspondence of the finite index lattice structure of the two groups when they have the same finite quotients. And we can say a bit more sometimes, like if the two groups are finally presented using log approximation, the groups are going to have like the same first L2 Betty number. And so like we can see like an L2 invariant from just by knowing that, okay, the two groups, I added this extra condition of being finally presented and saying that they have the same finite quotients. And we have some more open questions. Like if we have these two groups and we know that they have the same finite quotients, then question going back to Remslenikov, and one of them is the free group, finite generated free group is delta free. And we still do not know this as of this morning, whether is there a mystery group, right, whose quotients are all two generated finite groups, residually finite. Is there a mystery group like that that is not like the free group on two generators? We still do not know, but what we do know so far by work of I think Heike sapirane, the A state delta will be para-free. And what that means is that it has the same nilpotent quotients, or the same like nilpotent quotients as the finite generated free group. Okay. We also do not know this question, like if without extra hypothesis, like we do not know the answer to this question when gamma is a surface group. And yeah, so there is a lot that we do not know. So how do we think about finite quotients and how do we organize them? One way that is helpful to organize finite quotients, like instead of just thinking of it as a set of finite quotients, you can groupify by taking the inverse limit, right? And so like the profinite completion does exactly that. The profinite completion is going to be the inverse limit over all your finite index normal subgroups of the system of finite quotients. And in particular, having the same finite quotients, two groups have the same finite quotients exactly when they have the same profinite completion. And even though I'm writing this as a theorem, it of course it uses finite generation like really deeply, and even though I'm writing this as a statement, this is like a theorem of Dixon, Formanek, Holland, and Ribs. So for an arithmetic group, which is we should just really think like SLNZ sitting in SLNR, we have special kinds of finite quotients that come from reduction homomorphism, the images of reduction homomorphisms. Right, and so when you're thinking about Z, like Z surjects, like Z mod PZ, and in similar way, like you have SLNZ surjects, SLNZ mod PZ, and this is like what we call a congruence quotient, right? And we can organize this congruence quotients for an arithmetic group. We can think of taking like an inverse limit of the inverse of the system of congruence quotients, and in a sense, like just like in the intuition or just by definition, like you have like more finite index subgroups than you do have congruence subgroups of finite index, and so you're going to have this epimorphism from the profinite completion to the congruence completion. And in particular, we say that an arithmetic group has the congruence subgroup property when the profinite completion is isomorphic to the congruence completion, or in particular, every finite index subgroup contains a principal congruence subgroup. Yeah. Right, and it's like an old theorem of Bass, Milner, and Serre that SLNZ has congruence subgroup property for n bigger than or equal to 3, and it's like much older than that, but SL2Z does not. SL2Z is like virtually free, and its case is very different. And so this is like useful for the examples that we're thinking about right now. Okay, and so the theorem I'm talking about, to repeat, is that like we have like these pairs of groups indexed by the rational primes, like that have the same finite quotients, but one acts non-trivially on a simplicial tree and the other will always have a fixed point in any action on a tree. And so the idea is that the finite quotients, your action on finite sets, is not enough to tell you about actions on trees. Right? And so here are the groups in question, right? For a prime P, gamma P is going to be SL4 of with coefficients Z1 over P. And for delta P is going to be SL2 of a quaternion algebra intersected with like the product of SL4 ZL, where ZL is like the L-adic integers. And A is quaternion algebra over the rationals, like, and it's ramified. So what does this mean over here? What this means is that when you tensor at the real place, you should get the Hamiltonian quaternions. When you tensor at QP, you should get the unique division algebra over QP. So I'll call that HP. And when you tensor with QL for L not equal to this fixed prime P, you should get the 2x2 matrices over L. Okay, this is L not equal to P, right? And in particular, these choices are sufficient to fix for you an isomorphism type of like a quaternion algebra. And these are the groups that one of them is going to act on a tree. In fact, that one will be delta P, and the other one is going to have property FA. Okay. Right. And so what's the first thing we want to do? We want to show that these two groups have the same finite quotients. And the idea is that these are going to be like arithmetic groups. They're going to be like S arithmetic groups. In the gamma P is going to be an S arithmetic group in SL4R cross SL4QP. And delta P is going to be an S arithmetic group in SL4 of the Hamiltonian quaternions multiplied product with SL4 of like the unique division algebra over QP. And why are these going to be like arithmetic groups? Like the idea, the helpful idea, right, is that in particular, that even though Z1 over P is dense in R and in QP, it's discrete in the product. Right, and so that's the idea that underlies the reason why these two, or that's intuition, I should just say intuition for why we're going to have like these two groups be dense in each factor, but arithmetic subgroups like of the product. Okay, and then we use theorems to say that, like in particular, both groups have the congruent subgroup property, and so their profinite completions are going to be the same as their congruence completions, and their congruence completions are going to be the same. And so once we're at this stage where we've used like deep theorems of Basmiel-Nasser and Raghunathan that rely on like knowing what the Q rank of the group is, what the S rank of the group is, and what the and also know, and here also we need to know what the congruence completion is. Then we need to say that gamma P is going to be like a higher rank lattice because it's a lattice in a SL4R cross SL for QP, right? And in particular, every time it acts by affine isometries on a Hilbert space, there will be a fixed point. So this is like property T of Kashdan. And it's a theorem of Watatani that if you have this property T of Kashdan, like if every time you're acting on a Hilbert space by affine isometries, there's a fixed point, then every time you act on a tree, the group is also going to have a global fixed point. So this is like property T implies property FA. And so gamma P has property FA, right? However, on the other hand, the group delta P is going to be dense in SL2HP. And here we need to remember that this is like a division ring. There's like a skew field. There's like a local field, right? And so this dense subgroup is going to act without global fixed points on a P+1 regular tree. And this is in Serre's book. And so in particular, we have two groups. One has no actions on a tree, non-trivial actions, no non-trivial splittings. Another has splitting coming from action on tree, and these two groups have the same finite quotients. Okay, so that's like the idea of the proof, right? And so I have a question, right? Like the question that kind of motivated this problem, thinking about it in general, is like thinking about this question but for subclasses, like where in particular a conjecture of Brightson and Reid conjecture that all closed hyperbolic three-manifold groups should be determined by their finite quotients. And so this conjecture implies that, in particular, like finite quotients, this action on finite sets should be able to tell apart a Haken three-manifold from a non-Haken three-manifold, right? But so far, like, we have not been able to detect splitting of three-manifold groups equivalently by what I said earlier, detecting the existence of essential embedded surfaces, except in a few limited cases. Okay. And so this is still an open question, question that I think about a lot. So there's still a lot to be said. Okay. Thank you so much for your time. Yeah, thank you for listening. Yeah. And,
okay, let's thank Tam. Anyone have any questions? Again, feel free to ask either in the chat or unmute yourself and ask in person.
I have a question. Hi, Tam.
Yeah.
Just a curiosity, why did you state your theorem using property FA and not property T?
oh, so it was already known that property T is not a profinite invariant. Like this is like a theorem. It's due to Maniaka. If I'm not mistaken, Maniaka proved the property T is not a profinite invariant.
But this theorem is another proof of that, right? Because it's not only that it's a profinite invariant, it's that cannot the profinite completion cannot detect property T versus acting non-trivially on a simplicial tree.
Oh, so it is not. Like these examples are quite different from that case. Yeah.
I see. Thank you.
Yeah.
Any other questions? I have a quick one. So was it known beforehand whether these groups were profinitely rigid, that they weren't profinitely rigid even? Or is that new as well?
It was not known. It was not known beforehand.
And then could you also maybe say a few words about like why things are much easier, or why you can detect splittings often in the non-geometric world, like when you have a non-trivial JSJ decomposition?
The main difficulty so far is being able to tell apart an immersed surface subgroup from an embedded one. So because up to finite index, in particular, like Hegel proves, like it's in like, yeah, that when you have your immersed surface, right, you can lift to a finite shifted cover and to be embedded non-separating. So telling that difference between embedded and virtually embedded has been a tricky one.
Okay.
But in general, and the kicker, like the killer is like quasi-Fuchsian things. Like telling those apart, like we have tools, but like I don't know whether we've combined them well enough to be able to say in particular, to certify that the other three manifold group has a non-trivial splitting always. There are cases where we know, for example, if the discrete faithful, or if there's a representation with non-integral trace, using some of the p-adic machinery of Bright semifinals Reid Spitler, one can say that the other one has to have a splitting. If there is like a curve of characters in maybe the SL2C, PSL2C character variety, one can also detect that. And in the case that's not quasi-Fuchsian, in the case of a virtual fiber, that can also be, one can also say, yeah, the other three manifold has to be Haken as well. But outside of these very specific cases, like just like in general, recognizing a splitting is not, from finite quotient information, is not straightforward.
Yeah. Thank you very much. Any other questions? Okay, let's thank Tam again.